for a quick recap, assuming this thing works. Does it? So remember where we began? And then we said at slide 10 we were here. Now we are about here.
That's really going to go.
And then this is the way we're headed, right? It's pretty steep. But here are the things we've seen already for the whole business of Markov decision processes. First, we looked at Markov processes where you go only depends on where you are, not how you got there. And we saw that we can define different, there's the apparent or observed state of a system, and there's something called the information state of the system. So I can always take a system which is apparently not Markov and redefine it in terms of information states where the system becomes Markov. So when we had Glider, Flider's brother, who didn't like to turn back, we defined an information state as an edge and as a directed edge. And now suddenly the whole system is Markov. And regardless of how much history was considered in the progression, so long as the history was finite, you could always define the thing as Markov. Then we looked at Markov reward processes, where randomly wandering through the states will occasionally win you a reward. And so in this particular example, we saw that for the Markov reward process with the static fly and the spider, there are actually just 4 information states, where the information states are how far away, how many steps away the spider is from the fly. So this is where he's right at the fly, 1 length away, 2 lengths away, 3 lengths away, and so on. And we introduced the notion of a return and a reward. A reward is something that you got just immediately. A return was something that was the discounted reward all the way into the future, where you discounted the future more and more as it got further and further. The idea behind the discounting was that you thought of this return as one instance of something that you observed that you would base future predictions on, and you want to believe the futures. At any given time, you want to believe that something that happened many steps in the future is less likely to recur than something that happened immediately. So here, and then we introduced the notion of a Markov decision process, which was the same as a Markov reward process, except now the environment has agency. So, actually not the agent, the environment has, actually the agent decides, and the environment responds to the agent's actions, right? So here the spider could jump based on which way the fly could jump based on which way the spider decided to choose. So now the spider is not just randomly walking around the walls. The spider is actually taking decisive action, but the system nevertheless remains Markov. And the way we showed it was that this Markovian behavior now results from the random changes in the environment and no longer from the random behavior of the agent itself. So here, if the agent decided to move closer to the fly would jump, and depending on which current state the system was in, the entire process was in, the transition matrices changed. So we saw this as well. Here, for example, in this particular fly and spider problem, if the spider was 1 step away from the fly, if it moved towards the fly was always going to jump and move 1 step away. So with the probability of 1, the distance went from being this should have been, if it went closer to the fly with a probability of 1, the distance remained 1. If the spider moved away from the fly wouldn't move. So again, with the probability of 1, now the distance became 2. And we had similar transition definitions of the transition probabilities in the other cases. Yes?
In this case, how does he ever get the fly? If he moves when he moves closer?
So here is a beautiful problem of a policy, right? So here, if the spider is a distance of 1 away, the spider can decide whether to get closer or farther. So going closer is the wrong policy. So if he decides to go farther away, right? Actually, going closer is the wrong policy because he's going to stay at a distance of 1. If he goes away with a probability of 1, he becomes 2 steps apart, and then when he's at a distance of 2, and the next turn, he could then decide to go back towards the fly. And there's a 1/3 probability that the fly is actually going to land up in his mouth, right? So you see the notion of a policy emerging right over here, that now the spider gets to decide what action he must take, and the action is not the best action is not necessarily the greedy one. Simply reducing the distance to the fly is obviously the wrong thing to do over here when he's in this state, but is the right thing to do when he's in this state. So the policy becomes both state dependent, and the greedy policy is not always the best policy, as you can see, right? So I use this little example because all of these little facets of the problem kind of emerge from this very trivial example of a spider and a fly, something that doesn't always come across so cleanly when you look at more complex systems, right? You get what's happening, right? And the notion of a policy also emerges over here, that he has to decide, the spider has to decide which way he's going to move, and this decision is the spider's policy. And the optimal policy over here must be that if he's at a distance of 1, he must move away, but if he's at a distance of 2, he must move closer, and if he's at a distance of 3, it doesn't really matter what he does, right? So
If he's at the distance 3, he has to go closer, because if he doesn't, he's going to be stuck at.
So no, he actually does, yeah. He has to get.
It doesn't make sense.
No, there's only one action at a distance of 3.
If it's a cube.
There's no way of going further away
Since it's a cube.
since it's a cube.
Yeah, you're right.
Right. So that's what I meant by saying it doesn't really matter what he does is the same thing. It's deterministic at this point. His policy is deterministic. The system is not. Again, here's another very beautiful situation, right? All of which comes across in this tiny little problem. And that there's only one thing the spider can do when he's a distance of 3 away. But the system's state can change. There's a probability of 2/3 that the system will stay in state 3, and a probability of 1/3 that the system is going to switch to state 1. Right? So although the policy is deterministic. So this little example brings all of these little facets out. It's kind of pretty. And so we saw that the policy is the agent's choice of action in each state. The policy might be deterministic, it might even be stochastic. And what I mean by stochastic is that saying instead of choosing to just do this or just do this, the spider may decide that 1/3 of the time is going to take this action, 1/3 of the time is going to take the other action. In which case, again, now the entire process has 2 separate components adding to the stochasticity. One is the spider's choice of action, the other is the environment's response. Regardless, the entire system remains Markov. So then we saw the Bellman equations. The Bellman equations where I think it's worth drawing this figure here. So, oh wow. We always have a collection of invisible ink out here. Yes. So if the system had a bunch of different states, and let's say the system was currently in the state marked red, then we, wait a minute, said that the value of this state, each of these states has a value, and the value of being in this state is whatever reward you got over here plus the discounted reward, the discounted value of the next state. And the discounted value of the next state, since there were many ways of many different states you could possibly go to, it's going to be a weighted combination, discounted weighted combination of all of the values of the adjacent states plus the immediate reward. So Now again, because we have actually made the transition probabilities policy dependent or the action dependent, so if I define the value of the state for a particular action A, that is going to be whatever reward you got at that state for that action, plus, and then the value of the subsequent state. So that's whatever reward you got here for whatever the action you took over here, and then the discounted values of the adjacent states. You're looking at the values of wherever you could get to. So this was value of whatever state you got S prime that you got to, plus the probability of going to S prime from S given the action. You were summing over S prime and you had to discount it. So this is what we got, right? This was a simple that the you can represent the current value in terms of recurrence, but for any particular action, you can look at the reward. The value assigned to a particular action at a particular state was going to be whatever immediate reward you got for that action, plus the discounted expected values for wherever you would get to after having taken that action. And of course, you'd have to average this over all actions to decide the value of the current state. So this gave us the Bellman expectation for the state value equation, right? And so this is expressing the value in terms of values. We also saw that you can express the state action value in terms of state action values, but all of them are just different variants of this basic equation, right? So we've seen this already. And then we figured that there's something called an optimal policy which maximizes. So everybody's clear about all we've done so far, right? And then we saw there was something called an optimal policy that maximizes the expected discounted reward, total discounted reward, which is the expected return for every state, right? And I don't know how much if this was covered. There was something called an optimal policy theorem. There's an optimal policy theorem which says that there is a policy, or there are a set of policies under which every state has a value. The value of every state is better than the value that the state would have under any other policy. And this is kind of fairly trivial to prove. You can prove this using Banach's fixed point theorem. But the basic idea was that if you had two different policies, let's skip the proof. We won't have time for it. And then we spoke of the optimal policies themselves. So let's say you're in any particular state S. What is the best action to take? So the best action to take is going to be the action that gives you the largest return, right? Or largest expected return. So the action that has the largest state action value is the action to choose, because if you chose any other action, then the result then the expected benefit you're going to get is going to be less. So at each state you have a possible set of actions that you can take. So if you're at any given state S, then let's say you have four actions, then each of these actions has a expected value. And which action would be the most sensible one to take? The action that would be the most sensible one to take is the one for which this term is largest, because anything else is going to result in a lower expected gain, lower expected reward. So this was so it turns out that the optimal policy is really the greedy policy within every state, right? And if you're going to be following the optimal policy, then the value for the state is basically the state action value for the action that you're going to take deterministically, because the policy is now deterministic. The policy is no longer stochastic, right? And so with this, we ended up with the Bellman optimality equations, where you can define the optimal value in terms of optimal values, and we can define the optimal state action value in terms of optimal state action values. All of this was covered in the last class, I assume, right? So planning with an MDP, if somebody gave you the entire MDP, which is to say they gave you the state transitions, and they gave you the set of actions, they gave you the set of states, they gave you the set of rewards, everything. The process is entirely defined. The parameters of the process are entirely defined. Now you have two possible things you might want to do. First, so you want to find the optimal policy. Then we saw that there was a value-based solution where you can go through an iteration and find the values of all of the states based on the optimal policy, and then from that decide the optimal policy. And then we saw a policy-based solution which tried to find the optimal policy directly. So in the value-based solution, for any given policy, we'd find the values for all the states. And then given the values of all the states, you would go and reevaluate the policy and make greedy choices at each state. And then you could go back and reevaluate the value of the states, and then go back and pick the greedy policy again. So basically, first, given a policy, you could determine the values of all of the states using this little recursion. And so the policy iteration was, you first, given any policy, you use it's kind of odd. We're calling this the policy iteration when we're actually trying to, because we're actually trying to find a policy. So given any policy, you're going to find the optimal value for that policy, the state values for that policy. And from that policy, from those values, you're going to update your policy. Then from using the updated policy, you'd go back and find the values and then repeat this process. There was also the shortcut, which was the value iteration, where you didn't bother to estimate the policy at any point. You simply directly found the optimal value at each state iteratively. So each state here, all you did was, for any state, if you knew the optimal values of all of these guys, then you'd find that then you'd pick the best state, because your action would want you to go towards the best possible state and suck its value towards yourself. So each state simply inherits the cost of its best neighbor state. And if you keep repeating this process, eventually all of them will settle to give you an optimal value from which you can derive the optimal policy. So this was the value iteration. So this was the problem so far. Given all details of the Markov decision process, you want to compute the optimal value function. You want to compute the optimal action value function, and you want to compute the optimal policy. This was the task of planning. So planning is where you're given all the details, all the parameters of the Markov decision process, and you have to decide the optimal policy in each state. But in real life, nobody gives you the entire MDP. In real life, nobody is going to say, here are all the transition probabilities, here are the parameters of the model. So if nobody gives you all of the parameters of the model, what we've seen is if all of the parameters of the process are given to you, we have algorithms to compute the value for every state, compute the action values, the value of every state action pair, and to compute the optimal policy. But the real problem is nobody actually gives you the parameters of the Markov decision process. So in this case, how do we go about solving? The obvious solution is, okay, let me go ahead and first try to learn all of the parameters of the process. Because once I've done that, then mathematically I've reduced this to a known problem where I can actually solve the problem, right? Turns out that so that's actually one way of doing it. But ideally, you want to integrate search for the optimal policy along with trying to find the parameters of the model. So this is what we will call model-free reinforcement learning. When somebody gives you a model, we're going to call it planning. That's not reinforcement learning. We've spent 2 lectures talking about something completely unrelated to what we promised the topic was about. But it was required as a build-up to where we want to get. When we are not given the model, then we're going to call it reinforcement learning. So here we're still going to assume, now here there are 2 kinds of things. You're still going to assume that we know that we have a notion of a state, so we know what the states are. We are still going to assume that we have a notion of a reward, we know what the rewards are. What we don't know are how the entire system switches around between states. we don't know how the system behaves. We are able to observe the state, we are able to observe the reward, because obviously these are givens. If you're playing a game of chess, you can see the board. You know whether you're winning or losing. What you don't know is how your opponent behaves. If you're driving, you know what the traffic looks like for the most bit. You know whether you're getting home or not. What you don't know is what's going to happen next. So assuming that you know the state, you can observe the rewards, but you don't know the dynamics of the system. That's a fairly realistic thing to do, and that's closer to where most real life problems lie. And here again, we have two kinds of cross situations. How do you assign? You can decide on a policy. Given a policy, how do you decide? How do you determine what the values of the various states are for a policy? That's model-free prediction. And then how do you decide the optimal policy? That's model-free control. Again, these are just the model-free versions of the basic problem itself. So this is model-free reinforcement learning. How do you find the value of a policy without knowing the underlying MDP? And how do you find the optimal policy? The assumption, we know the states, we know the actions, and we can measure the rewards. We have no idea of the system dynamics. Just to be very clear about what we know and what we don't know. This is the situation that we're going to live in. Pretty much all the work that you see on Markov decision processes and reinforcement learning kind of work around this assumption, which is a very realistic assumption, right? So from our spider and fly problem, we can see the fly. You know the distance to the fly. You know what you can do, which direction you can walk in. You have no idea how the fly is going to respond, right? So let's look at this first problem. How do you find the value of a policy without knowing the underlying MDP? I give you a policy, and the policy is within any state. It tells you how you're going to behave, and you want to know the values of all of the states. So how would you actually go about doing this? Once we know how to do that, we're going to switch it around and see now how can we actually decide the optimal policy, right? So basically, in our problem, what is the value of being some distance d from the fly? We're going to have to decide this, right? So there are a bunch of different methods. There's Montecarlo learning, there's temporal difference learning, and in the temporal difference learning, you have many different options. This is really knowing how to perform reinforcement learning. Basically, is all about understanding specifically TD and TD lambda. So we'll spend time on this. And it turns out that if I just terminate the class after talking about TD, this will make life much easier for you if you ever take another lecture on reinforcement learning, because this is where we've sort of built up towards explaining where all of these things came from. So what is Montecarlo learning? So I give you a policy. Now what do I mean by giving you a policy? At each state, I tell you what action you're going to follow. The problem now is to determine what the value of each state is. So what would the obvious thing be? Just let the system run. You take an action at each state, the system is going to evolve, you find yourself in a new state. Then you take whatever action at that state based on the policy that you're given, and the system is going to evolve, you find yourself in a new state. All along you're getting rewards. So you're going to record several such episodes. You take actions according to this policy, and you note the states visited and the rewards that result. So what will happen is that you would start off, let's say, at the state, and you're going to take some action S. I don't have colors, so let me call this one, oh shit. Can you see this color by any chance? Okay, so let me call these states SA, B, C, D, and E, right? So you start off initially, you find yourself in state SA. You take some action A, and you get some reward RSA, right? Now, as a result, you're going to find yourself in some other state. Let's say you found yourself maybe you just found yourself again in state SA because the system could just return to the same state. So if you did this, then according to your policy, you're going to take the same action again. You get some reward, and then the system maybe finds you in SP, right? So then same thing happens. You're going to take whatever action your policy decides. You get this reward, and maybe the system finds you, puts you in state SC, and so on. So this sequence of state actions and rewards is going to happen, and all you're doing at each time is just letting the system evolve. You are using your agency to take the action that is desired, that is considered optimal, or to follow the policy that's considered optimal for that you have chosen for the current state at each state. So what will happen? You're going to find eventually in any given episode, you're going to find this sequence of observations, right? And now, what is the value function of any state? The value function of any state is the expected gain given that you're in the expected return given that you're in that state. So which is going to be so let's say you're in the state S at time t, then the value for that state is the expectation of this guy, the current return, the discounted return at the next instant, doubly discounted return 2 instants down, summing all the way into the future. So this expectation we're going to replace by statistical estimate. So let's say we have recorded many of these episodes. We've done this many times, right? And we're going to assume that each episode kind of ends at some point. We just say we call it over. You swallow the fly. Yeah.
This is all same policy?
Yeah, for the same policy, right? For the fixed policy. So now, after you've gone through all of these episodes, you can go back and scan each of these sequences and find the sample return at each point, right? When you were here, the sample return is going to be R12 plus gamma times R13 plus gamma squared times R14, and so on. That's how we define the sample return. So you could compute it here, you can compute it here, and so for every state, so observe that when I'm over here, the sample return is R13 plus gamma times R14, and so on, right? So now I can compute the sample return at each time. So I've gone over here, and what I have done is I have computed the sample return. Let me call this, oh gosh, this is terrible. So let's say they're all equally bad, aren't they? Why do they even keep them here? Okay. So let's say I have computed the sample return. I call this R1. I call these R2. I call this R3, right? So if I want to compute the expected estimate the value for state SA, what I would do is to pick all of the returns that correspond to state SA, which should be only these two guys, because these are the only two guys which correspond to state SA over here. This one actually corresponds to state SB, which is a different state, right? And average the lot. So basically all I would do over here is I'm going to pick all the instances of SA and the corresponding returns that I got at these times and average them. And that I'm going to call the value of the state SA, right? So you see what I'm doing over here. This is simple Monte Carlo learning. I've just let the system run. And then because the system has run, I have the observations all the way out into infinity at this point, right? And then, so at each time, I can compute the sample return. And then I could look at all the instances where I was in a particular state and average the sample returns from all of these times. And that I'm going to say is my estimated value for the state. I would do this for each of the states, right? So the very simple option is, so here is the little algorithm for it. Now observe that I can actually do this incrementally. So I'm going to go through, I'm going to be going, the way I would do it is, suppose I have the episode, I've already recorded the episode, I've computed the sample returns at each time. Now to update my statistics, I'm going to begin going left to right, And so when I see state SA, I will increment my count for state SA and increment my accumulator for the sample return, and keep doing this as I go left to right. And then when I'm done, I'm going to divide the total accumulated return by the number of times I visited the state after I have done this over all the episodes, right? And in fact, I can do this online, meaning after every episode, I can update my values. Not that it makes any difference to me, but I could update my values after every episode, right? Rather than wait all the way to the end, no big deal. So what Monte Carlo learning is doing is trying to learn explicitly from the from experience. And after a sufficiently large number of X episodes, in which all the states have been visited a sufficiently large number of times, we'll obtain good estimates for the value functions for all the states. And we can extend this for action value pairs, not just for state actions, right? So over here, for example, if my policy were random, then at this state, sometimes I would take action A, sometimes I would take some other action. So as I scan through this, I can actually use the same process, except my basic unit is no longer just the state, it's going to be the state action pair, and I can use the same thing to estimate state action values, right? So everybody clear about this, what I have done so far. This is the basis of pretty much everything. This is all it really takes, right? So this would be estimating the state action value. And you have the corresponding online version. Okay, so the nice thing about doing this simple, now this is a perfectly decent solution, right? Except, can you imagine using this to learn to play chess? Chess has 10 raised to 120 states. How many games would you have to play following a specific policy to even know the values of the states for that policy?
That's just one policy.
Yeah,
For
that's.
chess, there's many policies, right?
Yeah, so this is just for one policy. We're not even speaking of finding the optimal policy yet, right? It's a horrible thing to be doing, right? But thing is, you will eventually learn the right stuff. If you had infinite time and infinite patience and you had a partner who was willing to play infinite games with you, you'd eventually learn stuff, right? Can we do better? So here's what I do. Why do I have to wait to play the entire game and to play infinite games to update my policy, to update my values, right? Can I learn the value of a policy continuously and keep updating myself, and at some point when I find that the value is not changing anymore, I've already learned. I don't have to go through infinite episodes to actually decide that I've learned my policy, right? The benefit of doing things online is that when things stop changing, you're done. So if even for a given policy, you will know that you can determine your value fairly quickly. So, and you don't even need to wait for the entire episode. You don't need to wait for the game to be over. You could be learning your policy after each move. You could be learning the value of your policy after each move. How would you do this? So here's a very simple, let me just turn this off. Come on. So to do this, we take advantage of a very simple mathematical fact. So let's say I'm trying to compute the average of many samples, right? I can do this online. So the average of k samples can be written as k minus 1 times the average of the first k minus 1 samples plus the kth sample divided by k. This is fairly straightforward. Or I can refine it to say that the average of k samples is simply the average of k minus 1 samples plus a small adjustment, where the adjustment is the difference between the kth sample and the average of the previous k minus 1 samples divided by the total number of observations. And you will see that this has to converge very quickly. It's going to be converging as 1 over k, right? So as k becomes larger, the adjustment term is going to fall to 0. So you can actually I can write it more generally as the average of k samples is going to be the average of k minus 1 samples plus some small fraction alpha times the correction, where the correction is the difference between the kth sample and the average of the previous k minus 1 samples. And here's a little plot which shows you how this, with various values of alpha, they all sort of converge to the correct solution pretty quickly, right? And for large alphas, for alpha, as the alpha gets closer to 1, in the early stages, the variance tends to be high, but it tends to be correct on average. For small alphas in the early stages, the variance tends to be low, but it tends to be wrong. But eventually, they all converge to the proper solution, right? So this rule over here is what we're going to use for pretty much all of our estimation. So now here's what we were doing when we were trying to to estimate our value function. We were going through, when we performed Monte Carlo, we summed up the returns for all the instances where we actually visited that state and divided by the number of times we visited that state, right? I can redo that and write it like so. So when I'm doing something online, I can have a current estimate for the value for the state or the state action pair, and the next time I visit it, I'm going to make a small additive correction to this current estimate. And the additive correction is going to be the difference between the return that I saw at the next instant minus the current estimate times some correction term, right? This is exactly what we saw before. This hasn't solved my problem yet. This hasn't solved my problem yet because this g over here is the return, and g being the return, to compute the return, I must see all the way into the infinite future, which means I must have actually played the game to the end in the first place anyway. So it doesn't really help me directly, but it's going to help me in an interesting little way. This guy is the problem, right? So the way I will solve it is I'm going to say that so I've got some estimate for the value for this state. And when I get to this state, I'm going to make a correction which depends on the return, the observed return for the state. But then I know that the observed return for the state is simply the reward at the state plus the discounted return at the next instant, right? That's how we actually computed it. So I can say that the return at any time t is the reward at that time plus the discounted return at the next time. And I can write pretty much in general, yeah. So here's what I'm going to do. I'm going to replace this current return as the sum of the current reward plus the discounted return at the next time, right? Which is, what is the discounted return at the next time? Whatever it is. It's some return. But then I'm going to say that instead of using the discounted return at the next time, I'm going to use the discounted value of the state at the next time. So which means that I don't really need to have played the game all the way to the end. I'm just going to be looking at the value at the next time.
But you have multiple states, right? The next state has multiple states.
So let's say as I'm playing the game, right? So anytime I've played one state, so let's say from this place, you've taken an action, and then you've arrived at this state, right? Then you can make a correction to the guy one step back, right? Even without knowing what reward you got here. You just know what state you are at. That state has a value. So it's like a one-step look ahead, right? Or like a one-step correction behind.
Sorry, what is the value? Doesn't the value use the reward in the next at all those other states around it in order to calculate the value?
It does, but we're going to be saying that. So no, it looks at that's the expectation. Remember, we're still using Montecarlo, right?
Oh, okay. We're looking at one.
So everything now henceforth is based on Montecarlo because we don't know anything about the transition probabilities, right? We're estimating everything.
The original value.
Yeah, that's it, right? Yeah. So you're going to say, I was here, I took this action, I ended up here. So let me go back and correct the value for the state by saying the value for this state, saying my estimate for the return at this state is whatever reward I got over here plus the discounted value of the state that I ended up at, right? Just a one-step look ahead. So if once I do this, then this little equation gives us, suddenly becomes tractable, right? So you took a step and then went and corrected what happened one step behind, right? So this is called the time difference TD1, and because you're looking at you're taking one step ahead and you're going and you're looking back one. So you can say the updated value for the state is the current value plus a correction term, but the correction term is, this is simply the gain, right? And I'm going to write that as just this delta t, which is this correction term. And observe that the correction term is the reward plus, so why is it time difference? What it ends up being is when you came here, the actual correction term ended up being this reward plus the difference between the values of these two states. If these two states were the same, basically it's not going to even change, right? You're just going to get the reward. So here's what you get. So because you're looking at the difference in the values of two states one time instant apart, you end up with time difference of 1. So this is the TD error. And now, so you end up with this very simple, this is a true online update, that you're going to play the game, and every time you get to a state, you're going to look back and you're going to correct the value of update the value of the state you were at the last instant, right? We call this TD1. Now, this is like a look ahead of one state. But then here's what it is, right? This problem is, I can actually, this is guaranteed to give you the correct solution, right? But then there's something and in fact, there's a little example over here which I'll skip. You can show that when you're using this little look back and correct approach, very often you will get a better estimate than if you just played many games all the way to the end and then made your estimate.
Do you have to anneal the alpha over time, or the alpha term can just be a real number?
The alpha term can be a fixed number, right? So here, for example, we're using an alpha of 1. So in this example, we show that if I just played 8 games, right, where these are terminating states, and if I try to estimate the value of the value of the state A, then in the one example that I had where I began in the state A, all of the rewards were 0. So the value I would assign to state A is going to be 0. But then if you actually look at the actual model, you see that 75% of the time you're going to end up with a reward of 1. So the value of the state A really should be 3/4. It should not be 0, right? Now, if you use this TD1 process, now the TD1 process means that you can store all of these things and keep cycling over these data, right? You will end up, you'll actually end up getting 3/4 as the value for state A. So it actually works better. Now, but then, let's skip that and say what happened over here. We can actually do better than this guy, right? How can I do better than this guy? Here, when I wanted to compute the return for this fellow, I couldn't compute the actual return because the return would require me to look all the way into the infinite future. So instead, for the next state, instead of using the actual return over here, I use the expected return over here. And that's somewhat of a bit of a noise, right? So I can, instead of doing a one-step look ahead, I can do a two-step look ahead. So I can say that the return over here is this reward plus the discounted reward here plus the double discounted return down here, right? So which means that I'm going to take 2 steps, look back, and then I'm going to correct the value of the state 2 states behind. And that's a time difference of 2, right? Or I could do a time difference of 3. I can take 3 steps, look back, and say that the return over here is this reward plus this discounted reward plus the double discounted reward over here plus the expected return here, right? Or 4 times discounted expected return over here. So I can have larger and larger look aheads, and the longer the look ahead gets, the more accurate my estimate for the return is going to be, right? And so the limit, it's going to work best when I'm using the infinite look ahead, which gets me back to the original problem, which is, so TDN is with n step look ahead. This is exactly what I said.
But it's really a step back, then look ahead.
So no, so meaning step forward and correct back. It's correct back. I'm just walking with my face backwards and I'm correcting backwards all the time, right? So the problem here is that this works best if you work all the way to the infinite future, right? But if you're working all the way to the infinite future, why correct backward? You might as well correct forward. You haven't really gained anything, right? So here is the first observation that you end up with. So now there are a couple of different things that happen over here, right? When these guys are actually samples, they're not expectations. These are the actually observed rewards. And samples are going to be noisy. So as a result, when I have a one-step look ahead, my estimated return is going to be less noisy, less variant than if I'm looking at using an infinite look ahead. On the other hand, it's going to be more correct on average, right? So you have this bias variance trade-off. And the more look ahead you use, the greater the variance, but the lower the bias. So why do you actually so how much look ahead do we use? The infinite look ahead has the lowest bias, but it also has the largest variance. So instead of having to decide which one to use and which is best, why don't we simply use all of them, right? So what I'm going to do is I'm going to say I'm going to use with 1 minus lambda. So I can think of it this way, right? At this point, with 1 minus lambda, I'm going to use a one-step look ahead. And with lambda, I'm going to use whatever I get from the rest of the look ahead, right? So, but then the rest of the look ahead again, I'm going to, with 1 minus lambda, I'm going to use a two-step look ahead. And I'm going to have a factor of another lambda which looks at the rest of the future, right? And so the weighting I give is 1 minus lambda, 1 minus lambda times lambda, 1 minus lambda times lambda squared. The infinite future is lambda raised to infinity, right? And so I'm 1 minus lambda times lambda raised to infinity. Now, basically, as I'm looking further and further into the future, I'm giving that less and less weightage. So although I'm able to use some of the bias correction it gives me, I'm losing some of the variance that it adds. And this is kind of a cool little thing. Observe that these weights now sum to 1, right? But here is the really pretty thing that falls out. So this is what we will call TD lambda, where you're still looking using infinite look ahead, but instead of just using the infinite look ahead as one estimate, you're doing a weighted combination of all the look aheads into the infinite future. And when you do a weighted combination of all of the look aheads into the infinite future, then with an exponentially falling weight, this is going to be the resultant estimated return at each state, right? Remember, all of this is still within the random exploration. We are really not, we still don't know anything about the system. We are learning by observation, right? And then I can use the standard correction that we just saw. So all of this is fine, but then I still am back to where I began, namely that I have to have played the game into the infinite future. And I haven't really gained anything, right? But then here is what happens. This is the beautiful thing. If I'm looking infinitely into the future, right? Remember what really happened. When we were making corrections, I was not making a correction looking at the future. What was really happening was that when I was taking an n-step look ahead, I was taking n steps forward and then turning back and correcting something n steps in the past, right? And so as I kept walking backwards, I kept making corrections into the past. So what really happens is that although I'm thinking of it as saying I'm going to be, to find the estimate over here, I'm going to get 1 minus lambda times the estimate here plus 1 minus lambda times times lambda, the estimate here, and so on, the correct way to think about it is slightly different. So here, when I'm trying to estimate the return at time t, I'm getting 1 minus lambda times the reward at time t plus 1. I'm getting 1 minus lambda times lambda of the reward at time t plus 2, 1 minus lambda times lambda squared of the reward at time t plus 3, and so on. And then what happens when I take a step? I can actually flip the picture, right? So if I look at the reward at this time, t plus 7, which are all the states that it actually is making corrections to? So I can flip the picture and look at it backwards, right? My current reward is making a correction with 1 minus lambda to the immediately previous state. It's making a correction with 1 minus lambda times lambda to the state two time steps in the past. Remember, so instead of saying I'm going to be looking forward and making corrections, what we're really doing is you keep walking, and each time you get something, you make corrections to everything that has happened in the past. You take another step, you make all corrections to everything that's happened in the past. You take another step, you make corrections to everything that's happened in the past, right? And so if you look at this guy, when you come here, it's making a correction to this state, it's making a correction to this state, it's making a correction to all the states it has visited going into the past. And this is beautiful, right? So over here, now this gives you a nice little closed form formula. So let's say these are the 3 time instants where it visited the red state in the current game, right? So what is the correction this guy is going to make to the value of the red state? It's going to be RT times 1 minus lambda lambda plus RT times 1 minus lambda times lambda raised to 4 plus RT times 1 minus lambda times lambda raised to 6, right? So the sum of these 3 weights is the actual weight with which I'm multiplying RT to update the value of the red state. So this sum is what I will call an eligibility trace for the red state. And how can I compute the eligibility trace for any state? Anytime I visit a state, I just multiply. So anytime I take a step, I'm going to multiply the eligibility traces for all of the states by lambda, and by my gamma, which is my discount factor, and I'm going to add the add a 1 to the state that I currently am in. That's it, right? And so basically the arithmetic is kind of not, you can work it out, but the eligibility trace is really the sum of these guys. And that's easy to compute, you can work it out, right? So over here, when I come here, so if I'm currently in the red state, clearly I should only be updating the eligibility trace for the red state, right? So for the red state, I'd be multiplying all of these guys by lambda or lambda squared and then adding a 1 over here, right? For the rest of them, the eligibility trace must go down because they keep going further and further into the past without having been revisited. So that's all that happens. So let's skip the arithmetic over here. But then here is the beautiful thing that happens. Anytime I visit a new state, I get a reward, and then this reward is going to go back and it's going to correct the values for every state in my system. So here is the beautiful thing. Every time I make a step, I'm going to be correcting the values for all the states that I visited during the current game, right? And the way I'm going to update it, I'm going to add this corrective term, which is the time difference correction multiplied by the eligibility trace, right? And so and you expect the eligibility trace. Now this sort of goes back to what we were discussing in the very first lecture on reinforcement learning. Remember, we said that when I won the game in a game of chess, I'm going to go back and update the values of all the states that I visited. But states that I visited early on were going to get a much lesser green than states that I was at just before winning the game, right? And you expect that to actually be reflected through this eligibility trace, the E, which you expect that if a state has only been visited 50 moves ago, its eligibility trace is going to be really, really faint. A state that was visited only in the last move, that one's eligibility trace is going to be fairly high. And so you're naturally going to sort of you're going to distribute the current reward that you got over all of the states that you have seen so far, but the states are naturally going to get weighted in this manner. Right? And so we've done a big circle and come around after almost 2 weeks to what we saw in the very first lecture, within the first 10 minutes of the first lecture, how you would actually update the values for the state assigned to states in a game of chess. Right? Everybody here with me? I assume not. It's the end of the semester for everyone. So, anyway. So the whole magic of using this lambda weighting is that you manage to get the effect of infinite look ahead, but you're doing this through infinite look behind. Meaning every time you take a step, you're correcting all the way to the infinite past, as opposed to peering all the way into the infinite future to make an estimate for the current return. Right? So you're thinking of this in terms of corrections, and every time you take a step, you're going to correct the values of all the states that you visited leading up to this current step. And you're going to do this, you're going to update the values of all the states leading to the reward. So if lambda is 1, which is to say you don't actually, so what is the value of lambda over here? I just randomly chose a value of lambda, right? So if lambda is 1, it's like saying that I'm just going to assign everything to the infinite past and not looking at the, so if lambda is 1, I'm going to estimate my return based on the infinite past and only on the infinite past. If lambda is 0, I'm going to say I'm going to estimate my return based only on what happened immediately one step before. And for every other value of lambda, you're looking at all the steps in between, right? So what we want to do is to compute the values of all states given a policy, but no idea of the dynamics. And we've seen a Montecarlo and temporal difference solutions where the temporal difference is quicker to update and it's a better solution. And TD lambda actually emulates infinite look ahead. So this we've seen for a given policy how to estimate the values of all of the states. But then what do we really want to do? We want to learn the optimal policy, right? And so this is the final piece where everything falls together. Now, how would you actually estimate the optimal policy? Given a current policy, you already computed the values for all of the states or for all the state action pairs, right? Then it's very obvious. So at any time, you already have the value step, these state action values for all state action pairs. So at any state, you could literally just choose a greedy policy and follow that policy and then make further estimates. The problem, of course, is that it's not so simple. So first thing, everything that we saw so far computes the value functions of states. What you really want to compute is the value function of state action pairs. And that kinds of blows things up, but without it we can't really work, right? So, and then if you're given if you're given state action pairs, then it's easy enough to find an optimal policy, right? That's why we're going to be working with state action pairs. So what happens? Here's what I can do. I can start off with some initial policy that I'm following, right? And based on some initial policy, I can also start off with some initial estimates for the values for all state action values. Then I make a first step. As soon as I make my first step, I've updated all of my state action values because I'm doing TD lambda, right? So as I keep moving backwards, I'm correcting my state action values for every state action pair. And then based on the updated state action values, I can update my policy. And then use that policy and then make my next step and keep doing this. And you would expect that as I keep doing this, eventually I'm going to learn more and more. I'm going to arrive at a more and more optimal policy. The problem, of course, with this is that it's greedy, right? So if you have a deterministic policy to begin with, you're never going to be able to assign values to state actions that are not part of your policy. If your policy says when I'm in this particular state I always move the pawn, the only thing that you're ever going to be able to compute is the value of moving a pawn when you're in that state. You're never going to be able to assign a value for moving a knight, because that's never going to be observed. The value that you're going to assign it is going to remain 0, right? So as a result, I'd say you run the risk of positive feedback. You only learn to evaluate your current policy. You don't learn to update your policy. So here's what we will do. You will have some policy. You say when I'm in this particular position, I'm going to move the pawn. That's my policy, but I'm going to follow the policy 50% of the time. The other 50% of the time, I'll randomly choose one of the other coins I can move and move it, right? It may not be the optimal thing to do, but because my initial policy itself might be crappy, right? This gives me the best chance of discovering a new policy that's better than mine, and to evaluate that new policy as well. Now what you can do is this epsilon can actually be annealed, and you can reduce it over time, but in the beginning you can have a very high exploration. So this is the standard exploitation versus exploration strategy, right? So this is what we'll call an epsilon greedy policy. So this was called the greedy in the limit with infinite exploration of Montecarlo. Now everything that we are talking about, you're going to actually do the TD version, and that you're always going to be correcting all the way backwards, right? The only thing is that, so I can actually skip this arithmetic. You're going to be computing the epsilon greedy policy for each state. You're going to be using an epsilon greedy policy, and this is the thing that comes in. So the online version, if you're looking at just a one-step look ahead, the algorithm is called SARSA, where you start over here, use your current policy to get to here, and then correct the value one step back. So what is really happening is you're at a state, you take an action, you get a reward, then you arrive at a new state, you choose a new action, right? Because you're always updating state action pairs, state action values. So if you read these 5 characters in series, it's SARSA. So the algorithm is called SARSA, right? And it's a one-step correction, literally. You're always walking forwards, and making a correction only to the state action that you just were at immediately in the past, yeah.
So our policy is changing over time because as we look back, we're changing the value. So we would have, had we been in that state, we would have made a different decision because we now have a different value associated with that state.
Yes.
Is that what the whole point of the look back is?
Otherwise your policy is never, no, the point is you're trying to assign values to state action pairs, and you are trying to find an optimal policy. You're starting with some policy because you don't know the transition probabilities. So you have to let the system move you. For the system to move you, you have to take an action. Action comes from a policy.
Okay. So I understand that we have these states, these actions. What does a policy actually look like?
A policy is literally going to say something like, the spider. If I'm a distance of 3 away, I'm going to move towards the fly.
So, is it simple rule-based policy?
A policy could even be a function where you take a bunch of measurements, throw it into a neural network, for instance, and it gives you a probability distribution over possible actions, say, right? And the policy can be stochastic, right, or deterministic. Or your policy could be, I'm going to put all of these values into a network. It gives me a distribution. I'm going to pick the largest one, the output for which it assigns the maximum amount. So what would happen over here is that you'd start off with some initial policy. You start off with some initial state. You take an action according to your current policy, where you take maybe some measurements. If you are playing a chessboard, you can take a picture of the board, pass it into the neural network with an indication of where you currently are and what coins could be moved, for instance, right? And it's going to give you some distribution over those coins. You pick the coin for which you have the move for which the output is largest. And that's a totally random policy, right? And then you get a reward, which might be 0 because it's the beginning of the game. But assuming that you've initially assigned some random rewards to all of the states, you get some reward. You move into a new state, right? Then moving into the new state, you're going to use the same policy method, and then you're going to choose a new action, right? So you were at a state, you took an action, you got a reward, you ended up in a new state, you got a new action, right? Then what you would do is you would say that, okay, based on this I can look back and then I can update the state action value that I got for this combination, right? So now I have a state action pair and an updated value. I could, for instance, go back and even use that to retrain my neural network to learn that particular relationship better, right? Or make a table. Everything that we've been talking about so far actually is in terms of tables. But
instead of argmax of QA, SA, you pick a neural network to decide the optimal.
So that would be typically what we've been talking about is using tables. But if you replace the table with networks or whatever, right? That's basically what people really do.
Another question. So in the equation here, why aren't you using the value for S prime as the value for next state? Instead you use the Q S prime A prime?
So no, so I'm looking at the state action values. I'm not looking at states anymore. For policies, I need state action values.
But if you keep another set of values, wouldn't the value for S prime be better used in the equation?
So I could actually keep a value for the state as opposed to a value for the state action. And yes, that would so in that case I'd be retaining both values and state action value.
You can still keep the SA pair, but you can use the S prime, the next state value is
instead of the state action. You're absolutely right. Right. Also done. Yeah. I mean, I'm just explaining everything in terms of essays, right? So, if the point is that the policy is deterministic, then state action value and state and value are going to be the same thing.
yes.
Right? So that's your standard source. I mean, when you would have some policy and this is going to be your update rule, and you could correct it to use the values instead of the state action values. But it's pretty much exactly what you said. You have a policy, you're going to follow it some fraction of the time, and the rest of the time you're going to randomly choose amongst the states that you're allowed to go to, right? So Sarsa lambda is like, it's TD lambda, right? Instead of looking back and correcting just one, you're going to be correcting all the way to the back. But this is exactly the same as what you did. The only thing that changes is that you keep updating your policies all the time, right? So now here is the beautiful thing, right? If I fix a policy, and if I'm updating my policy, and I'm learning about it, I'm assuming that I'm actually following a policy and I'm learning the value for that policy. But here is where things change, right? So what I could do is, I have a state action value, right? But then I can, so the reason you actually look at state action, so observe over here that when I do Sarsa, this action, I may have taken this action, but I may have chosen this action, I have not actually taken it, right? I could have chosen, so here I'm actually given two choices, the action that I choose and the action that I take. So I can have a hypothetical action, I can have a real action, right? And if I choose, so now I can have two different policies. If I choose policy B, the action I would have chosen is A2 hat. If I use policy A, the action I'm going to choose is A2, right? So if I use this guy, S2 A2 hat over here, which policy am I evaluating? I'm always evaluating the hypothetical policy. Correct? So this is the beauty of the whole thing, that I could be playing the game according to one policy, but I could be updating the values for a different policy. So what I could also be doing is I could be watching you play chess and you're a crappy player, right? But I could be learning about my game, right? And this is the beautiful part of it, in the sense that, so I say, okay, you know, Andrew moved a pawn. I wouldn't have moved a pawn, but he moved a pawn. That's fine, right? So that's what he did over here. And then, so then he ended up in this state. And in this state, I would move the knight. And what is going to be, so given that I would move the knight, I have a new value based on moving the knight, right? So Andrew moved the pawn over here, ended up at S2. Here I would move the knight. So now, having moved the pawn and gotten the reward R2, I end up with the future expected state action value assigned to, associated with S2 A2 hat, right? And so that means based on this, I can go back and make corrections to my own policy's value for QA, S1A1.
As to how good it was to actually move the pawn.
Yes, right? And so even if according to my, so I might find that, you know, although you did something that I would not have done, I surprisingly find myself in a situation where according to my policy it's a pretty good position to be in. Then I should go back and update my own estimate of how good it is to have moved the pawn in the previous state, right? So I can go back and update my values based on watching you play, although you are following your policy and I'm evaluating mine.
Because you are not evaluating policy, just evaluating the state action pair, so it doesn't matter who plays it.
Yeah, exactly. No, but you're evaluating you're updating the values of the state action pairs based on who, regardless of who plays it.
And then the policy, it's your so you can argue you can whatever.
Oh, yeah, exactly, right? So, and it's very beautiful. The whole thing kind of, yes.
If the policy you're comparing with those like better, strictly better policy, won't your policy eventually drift towards that policy? You'll basically update to their learning rules over time.
If they're strictly better, right?
You will see the value for
No, but the what is that not all, if it's not, it may not be strictly better, right? The point is, yes, if they're strictly better, you're going to sort of drift towards their policy. But
if it's not strictly
unless
better,
you have a crappy policy rule, say arg means the
yeah, right. So the point is, so all sorts of things can happen.
I'm just thinking about the dynamics.
Yeah, you're right. You're right. But the point.
What kind of things does your policy learn? It's going to be drifting if it's better or if it's worse.
The point is, you don't even need to change your policy, right? You can just say that, you know, you can just assign. Actually, yeah. So all sorts of things can happen. The key point is that you could be following one policy and learning about some other policy. And you can, in fact, you could be doing this simultaneously for 10 different policies. Because there's no restriction on saying this is the only policy I'm evaluating over here. I can say I have a different policy, and that would have resulted in some other action over here, and based on that policy has this new updated value, right? And so you can actually be evaluating multiple policies while playing one game. It's kind of pretty. So which sort of now, so you're still going to be kind of stuck over here. If this guy over here, if Andrew always plays a very deterministic policy, I'm not going to learn very much about my policy either, right? So the best thing for Andrew to be doing is also to be using a exploration versus exploitation so that I can learn about mine, right? Or I can be using an exploration versus exploitation and simultaneously updating several other policies. If my policy stays deterministic, I'm not going to do that. So there's the whole exploration and exploitation aspect to it which comes in. This is what we call Q-learning, right? From any state action pair, you accept a reward, you make a transition, find the best action for S prime, right? Use it to update QSA. According to your current policy, but then actually follow a different action policy to actually decide what action you're going to take, right? This business of learning about one policy while following a different policy, if the two are related by only through this epsilon greedy action, you call it Q-learning. But you can actually also call it, if the two are completely different, you call it off-policy learning, right? So you could say over here that this guy is obtained from a deterministic policy, but this one is through the epsilon greedy. So they are two different policies, right? Related policies. So that's Q-learning. And Q-learning again can have the one-step look ahead or infinite one-step look back, infinite look back. All of these are the same thing. So I'm not actually going through the math, but I think the ideas are very straightforward, right? The nice thing about it is that although it looks so complicated and very fancy, if you sit back and think about it, it's all almost obvious. It makes sense. It just makes sense, right? The key is to be able to visualize the whole thing. And I'm kind of hoping the spider and fly example helped you visualize stuff. So Q-learning is currently the most popular reinforcement learning algorithm. I haven't actually covered a whole lot of stuff. How you approximate value functions, continuous state spaces, deep Q-learning where you use neural networks to learn stuff. There's something called action replay. Now here is the lovely thing, right? So this is, what do I mean by action replay? Suppose I've actually observed a series of things, right? I can play a game. I can observe Andrew play one game and just go through that game and learn about my policy, which is very different from Andrew's policy. But you know what? I can go back and using my updated policy, I can keep going back through that one game that you played and keep updating my own policy because there's nothing stopping me from doing that. I went through the game once. I updated all of my state action values. Then I can go back and revisit your game and do the whole thing. You never played another game. I just went back and revisited it because I got a specific sequence of state action values and rewards, right? And that's what we will call action replay, that you actually remember some things and then go back and revisit it to correct yourself. And it makes sense in the sense that you got all the way to the end of the game, you got some action value pair, action values that you've estimated, but then you say, hey, this doesn't make sense. This doesn't quite match what we saw in the beginning of the game. Things have drifted, so let me go back and re-update my stuff. And you can keep cycling through, right? And you can cycle through many such games. So this is what is called action replay. Once you put all these arithmetic down, it's magic how many different things you can actually do. The fact that you can be doing one thing and evaluating a different thing opens up all of these different options, right? And so that's action replay. And then, of course, there's the business of how do you actually apply it to a real problem. But it's 10:18. It's the last class. I'm going to stop here.
Okay, perfect.
And please, folks, we worked hard for the course. My TAs have done an amazing job. Sometimes we've been, short sometimes, but for the most part, it's been a lot of effort by a lot of people. Do us a favor. I've asked for feedback on how the homeworks can be improved on Piazza. Please post, and please post your FCs at the faculty course evaluations. Right? I don't know if they ask you to evaluate the TAs, but I'd appreciate it if you did. If they do ask you, right. They've just been amazing.